All right, so chapter 9 is all about air conditioning. Ever wonder about how your air conditioner works? Well, we're going to talk about it. So, air conditioning is a system for controlling the humidity, ventilation, and temperature in a room, building, or vehicle, typically to maintain a cool atmosphere in warm conditions. Because down here in the South, who wants to live without ACR? Anybody? Raise your hand. You know you want to live in the heat and the humidity and the miserability that comes every summer in Alabama or in the South in general, right? Everybody wants to live in the miserable conditions. Anybody else has started to wonder these days about exactly how they lived without it? Does anybody else wonder how they lived without ACR in the South? Because I can't figure it out. All right, refrigeration is the process of moving heat from one location to another in controlled conditions. So essentially, air conditioning is about controlling all of it. Refrigeration is just trying to remove all the heat. So air conditioning is the process of removing the heat and humidity from a room, building, or vehicle. They have already said that. Refrigeration is removing the heat, but not the humidity from a confined space. Kind of like if you ever open your refrigerator or your freezer, you get little bits of ice in some places in the freezer, and it's very wet sometimes in the refrigerator, right? It has its own humidity. What is humidity, by the way? Does anybody know what that term actually means? Exactly, it's the amount of moisture in the air. Sometimes you actually need that moisture, right? The good thing about it can be in the summer, you don't see a lot of static cling, right? Humidity can dampen that down. But these are both predominantly used as closed systems. Why? Because the stuff we use to do it, it's not exactly environmentally friendly. All right, so these are a couple of systems. Both of them are ACR. This one's a very simplified version. This is the one that's a little more complex looking, but it's the same thing. And it all starts with a compressor. Okay? The compressor pushes warm air into the condenser. The condenser draws the heat out, and the warm air becomes a liquid. Okay? This is done in your car through your what? Huh? Not so much the compressor. You're doing it in the condenser or through your what? What's one of the major parts of your car that you probably take for granted? Your radiator. What is your radiator meant to do, guys? Does anybody know? It takes hot fluid and hot everything. It flows it literally through the tubes, just like this, whereby the little metal pieces help pull the heat and radiate it out. Meanwhile, when you're driving, you're pushing air through that radiator to help cool things. And when you're sitting still, you have that radiator fan that does the same. Nobody's ever had to replace a radiator before? It's a bit of a pain. It's in the very front of your car. Matter of fact, if you break your grill, chances are you'll break your radiator. Because it's almost literally right there. It has very little protection. All right. So once it pushes the hot air into the condenser turns it into a liquid. The liquid then moves through the system, and once it exits, okay, it is not as hot as it used to be, but it's still kind of warm. It is pushed through a dryer, be pushed through a metering device, and then it goes to your evaporator, okay, which is continuing to pull that heat off. So we do not want heat in our system. Why? Anybody ever have a car overheat? What happens when it overheats? It shuts it down. Okay. If you've ever seen the old movies where they had the crank cars and they had to continually pour water into the spout on the very front of the car, anybody remember seeing those kind of old movies and stuff? Probably got shown in school every now and then as a teaching video. Um, that's the radiator, and what they're trying to do is keep the radiator cool. Once you've cooled the radiator, you're trying to keep it cool because otherwise the car overheats, and it's not ever good when a car overheats. You can damage all sorts of innards whenever that happens. Kind of like when you overheat. When you overheat, what happens? Heat stroke. Your whole body can collapse, right? Same thing for anything else. Overheat anything, go into total structural collapse, and it does not work anymore. So you go through the evaporator, it goes back into being from a liquid to air, or basically it returns into being a non-liquidated state, we'll put it that way. At which point it is pushed back up into the compressor, where it is compressed, reheated, and pushed back out into the system. Okay.
If you live in a hot...
Me, okay, seriously, where's the other end of this line? I don't know where the end of that one is, so I can put the speakers on, but instead we'll turn that on.
part of the country, it's probably hard to imagine surviving without an air conditioner. And if you have an air conditioner, then you have a big box like this in the backyard. Have you ever wondered what it's doing back here? The basic idea behind any air conditioner is evaporation. When a liquid evaporates, it feels cool. If you put alcohol on your skin, you can feel the coolness as it evaporates. An air conditioner contains a liquid that evaporates, a lot like alcohol, but it evaporates at a lot lower temperature. The liquid evaporates inside the house. It evaporates inside a set of metal coils, and the liquid makes the coils extremely cold. A fan blows air across the coils, and that air is what cools your house down. When it evaporates, the liquid turns into a gas. To turn that gas back into a liquid, you use a compressor. The compressor squeezes the gas, but it gets really hot in the process. The fan and the coils in the backyard let the air conditioner blow the heat off the liquid. That liquid goes back into the house to evaporate again. It's a continuous cycle with the gas turning into a liquid, turning back into a gas. Your house is getting cool the entire time. So that's how an air conditioner works. I'm Marshall Brain, and that's how stuff works.
Okay. So that's the very basics of how all that works. You go from liquid to gas, the meantime, you're also exchanging constantly and consistently the heat that is generated. Okay? The way a never mind. We'll move on to it. An ACR system does not draw cool air into a space, but draws heat from the space. You're trying to remove heat. Why? Because we don't like heat in Alabama, especially summer. It gets too hot. Right? Every single one of us, whenever we're in summer, we're all trying to look for the coolest place to chill. Especially when the humidity gets to being 100%, right? So it works on the principle of evaporation. When gases are compressed enough and then cooled, they turn into a liquid. When a liquid turns into a gas or vapor, it can draw heat with the process. That's the basics of how you sweat and why you sweat, right? The human body's personal built-in air conditioning unit is your sweat. The way it's supposed to work whenever it's not 100% humidity and you don't feel like you're walking into a shower when you walk outside is that you're supposed to sweat, and then when that evaporates, it's supposed to cool you down. In high humidity, that's not such a possibility, right? All that tends to stick directly to your skin. It doesn't evaporate and you cannot cool down. That is why that works that way. Okay? So theoretically, the way it should work and the way it works in most other areas of the world is you sweat, it evaporates, it cools you down. It's pulling heat from your skin and your body to allow you to remain at a more consistent temperature. Again, that doesn't work so well down here where it's so humid that you can't walk outside without screaming or feeling like you're breathing water instead of air. Okay? So when a liquid turns into a gas or vapor, it draws the heat with the process. It's done with sweat. It's the process of the water misters that we used to play with as kids that never worked, right? Y'all know what I'm talking about? The little fans with the water mister that never worked right. Seems the batteries were always dead and it never could miss for the crap. In ACR systems, the gas needs to be compressed and condensed and then evaporated. It must be able to repeat the cycle over and over in a very short time period. Refrigeration, the term we typically use is Freon. Freon is, funny enough, I've had a lot of ACR guys tell me Freon is not what it's called. Because Freon is a very, very specific product. It is not, it comes down to this. Freon is a product. There are other products of similar type. Why it's Freon is because it's one of the first ones that was on the market. It's trademarked and owned by DuPont. It is a fluorocarbon-based refrigerant with several R ratings. Now, can you use the same refrigerant in your house in your car, or vice versa? Everybody shake your head no. Because as tempting as it is, you can't. They have two different R values entirely. And if you do that, the guy that ends up having to come out and repair your system will kill you. It's not good for your car or your house to mix them. There's a specific R rating that's supposed to be for your house, and there's a very specific R rating that's supposed to be for your car. Your car is, I think, 134, but don't quote me on that particular one. basic components, you have a compressor. Now we know what a compressor is, right? It takes outside air and turns it into what? It squeezes it down, right? Well, in this, it does the same thing. The pump that moves the compresses the gas from the evaporator. So it's taking all that gas and it's bringing it back together, right? Condensers, these change compressed gas into a liquid. It transfers the heat from the space to the outside, or called a heat exchanger. Okay? Again, it's the whole purpose of try to draw heat out, right? Trapped heat is no good. You have refrigerant. It is typically referred to as Freon, but Freon is a very specific product. Don't ever utter those words around the ACR guys. They tend to not like you very much afterwards. Seriously, I've been corrected. I've had more than a few ACR guys in this class, and they always sit there and go, no, it's not a Freon, it's refrigerant. 90% of the world calls it Freon. Sorry. You have a receiver dryer. This stores the refrigerant. You have also got what are called expansion valves. All right, and this passes liquid into the evaporator at a controlled rate, also called the metering valve. Okay? Because we don't want to just have it uncontrolled, because you could end up with too much at one end and not enough at the other. Right? So what you have to do is be very careful in how you move it. So evaporator, this turns liquid into gas. It removes the heat and humidity. Again, something we're grateful for here in the South, because heat and humidity are killers, right? Air or water passes through the evaporator, removing the heat. Okay? You might have also heard it called a chiller. Anybody ever heard of a chiller? Again, chiller, not thriller. Oh, come on, I was trying to make a joke. All right. But it's called a chiller. All right, what it is supposed to do is exactly what we said. It's supposed to remove heat. Heat exchangers. This transfers the heat from the condenser. It removes the heat from air or water that is absorbed moving through the evaporator. You also have controls. This controls the whole process. Try not to repeat myself too much here, guys. ACR diagrams. So essentially you have all three types of diagrams that we have talked about previously, typically are stacked in ACR. All right, truly think about the air conditioning, refrigeration in your house, right? If you don't know where the electrical is, let me introduce you to the thermostat, right? Piping, you have got to move everything to some place or another, right? If only in through the ductwork. Then you have the fluid power, which we've basically been talking about this whole time. Hydraulics would be working with that liquid Freon. Okay, pneumatics would be working with the aerosolized Freon, right? So it's made up of several subsystems. We got 4 subsystems. So you have refrigeration, air, water, and control. Refrigeration is where the heat is pulled out. Air is when everything is aerosolized. Water is whenever it's liquidized. And then you have the electrical, which is the control. All right. So in the refrigeration subsystem, you have heat exchangers. The textbook completely ignores the fact that residential, small commercial, and vehicle air conditioning systems. Why? Because it's trying to look at mostly major commercial. There's a couple of different ways that it's done. In some of the bigger buildings, some of the older systems, you have actually got cooling towers. Okay. In most small applications, like your house, how many of you even know where your outside ACR unit is? Your air conditioning unit outside. It's the giant metal box with the little fan that spins in the top. That looks like it's nothing but a dirt magnet, right? So you have to sit there and ask yourself, how exactly are you supposed to get in there to clean that out because it's got 1,001 bits of leaves and stuff in it, right? Everybody knows where that big metal box is. What that big metal box is supposed to do is it pulls all the heat in the system in your house outside to get rid of the heat. Just like your radiator in your car pulls all the heat into it and tries to release it into the air and pull enough cool air through your car to keep your radiator cool. So you don't want your radiator to overheat. Not down here, not generally. Radiators that freeze, typically what you've done instead of using refrigerant material, which is a lot harder to freeze than anything else, is typically you've used water instead. So if your radiator is frozen, you got something in there that's not supposed to be there. You can, but again, that's generally because something's in there that shouldn't be. Refrigerant materials typically don't freeze. They just really don't, typically. If you get water in your system, yeah, you can freeze that sucker in just like a pipe. I mean, you've ever had to deal with a frozen pipe, right? It's not common here in Alabama because why? We don't get cold enough to do it. We don't get cold enough and stay cold enough that anything really freezes down here, right? But in places in the north, yes, you can have some issues with that. Generally, they're not worried so much about ACR as they are about heat and trying to put as much heat and radiating heat into their homes. Well, honey, they don't get 100% humidity and 80s and 90s that feel like hundreds and 110s. Yeah, I have visited the north. I don't ever want to live up there because they have to deal with ice and snow. We have to deal with heat and humidity. I know which one I would rather deal with. The thing that's much less likely to cause your car to slip around and kill you. Okay. So they're not worried so much in those systems about trying to cool things. Most refrigerants, again, they have a very, very high freeze point most of the time. They specifically tend to develop a lot of these products for the areas they're put in. So down here in the South, you don't really have to worry about stuff freezing, so you're not really going to worry about your product freezing. Boiling, yes. Freezing, no. Up north, you have to worry about things freezing a lot more, so you're going to use a different product. They complain about 90-degree heat and 10% humidity sometimes. We complain about 90-degree heat and 100% humidity that makes it feel like, oh my God, I'm about to die. Control subsystems, again, that's going to be dealing strictly with a lot of electrical. So refrigeration is the most important part of the ACR. Diagrams can be orthographic or isometric because we're dealing with a lot of piping, right? This is where you typically see piping and hydraulics, pneumatics kind of work together. Why? Because you end up with dealing with a lot of hydraulics, pneumatics, but at the same time you're dealing with having to pipe it all. Okay. So industrial can be shown either in single line or isometric. Training diagrams are usually shown as a double line. A lot of symbols can be different from simple piping systems simply because they might be a specialty pipe, right? It might be something specialty that is strictly for that particular use. If you've ever gone to the hardware store and started poking around in the hardware store, right? There's different areas where it's very specific to a trade. You know what I mean? All right. So refrigeration lines, fittings, and joint symbols, again, they have some that are very specific to the trade. You still have caps mean caps. You have connections that are connections. But the way some of these can be combined can be a little bit different. In small residential, I'll tell you right now, you don't typically do a lot of welding. You will not see a lot of welders in home construction. Why? Oh, huh? Well, it's too permanent, A, but B, it goes all behind the walls, so you really do not want a permanent connection if you have to break a wall open. It's just not necessary. Most of the time, you're not dealing with big, heavy lines that if it busts, they'll destroy everything in a plant. You're dealing with smaller lines. Most lines in your house, yeah, I feel pretty comfortable saying this. Most lines in your house are not over about 3 to 4 inches wide. Okay? They're not. Why? Because they don't need to be. Huh? Diameter wise, you won't see a pipe bigger than about that in your house. If it is, it's probably the waistline. That is about the biggest pipe you have in your house is your waistline. So most of the time with those kind of joints being smaller, welding would be all but impossible. Simply because the metal would get too hot and start trying to melt into itself. So most of the time what we tend to do with things in your house is we do a lot of brazing, soldering, things like that. Because it still creates that permanent connection, still creates the seal. And most of the time you don't want to try and break those seals because it's a pain in the rear. Generally, if you are having to do work in the house, you're going to cut the pipe on either side of a fitting and just let it go and put in new connections. But a lot of brazing and soldering is done in houses. You will not see it done so much in major applications because in more major applications, let's say a factory or something, those are typically welded because you really do not want those ever coming apart if you can help it. In the house, you have to occasionally replace pipes. Most major applications, you really don't want to have to replace it if you can help it. Um, so yeah. So different kinds of piping. You have discharge lines, liquid lines, and suction lines. In the discharge line, this goes from the compressor to the condenser. This typically carries hot gas between 120 and 350 at 100 to 400 psi. Put it this way, if you get a hole in that, do not ever put your hand near that. That is not boiling water. That is steam point going to take your hand off water. That is second to third degree burns. Okay? If you ever see a discharge line that is ruptured or has some sort of a hole in it, walk away, call somebody that can deal with it, or turn off where you know the pressure is going to be. Because that hot gas is not going to be a friend of yours. Okay? If you suspect that you're looking at a leak, what should you do with pneumatics? Huh? How do you find a leak with pneumatics? Huh? Well, you can hear it sometimes. No, 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 you don't ever want to do that. Anybody know how they find a hole in your tire? No, you use soapy water. If you're looking for a leak, you use soapy water. Why? Because it blows bubbles. You don't want to put any part of you near this. Okay? You put soapy water on it to find where the leak is because it'll blow bubbles at you.
Pressurize the tank, and that way, like the water's like or the air's expanding like inside the tank. When you spray this soapy water on it, the bubbles, it makes bubbles because the air's obviously taking out of it.
Yeah.
So you might really just go on water, yeah, you're putting air in it.
Yeah, most of the time, have you ever had a flat tire where it's just like you ran over like a nail or something? Most of the time, to find where that nail might have been, what they'll typically do is just take out a bottle of soapy water, and we're talking like Dawn dish detergent kind of water. And they just start spraying it around your tire, and what they're looking for is something to blow a bubble out. And it's just a good way of visually seeing it instead of trying to run your fingers over it and possibly tearing up your skin. If you consider that most refrigerant material is what you're dealing with in this particular case, you do not want what might be aerosolized in that air that can get under your skin. It can cause bubbles and all sorts of other stuff that would not be very good for you. Because that also carries a lot of chemicals to it and everything else to keep it aerosolized. So you do not want to sit there and put your finger over something that's got 400 psi that's directly injecting who knows what into your skin. So the best way, if you have something like that, take a little soapy water if you suspect there's a leak and it can show up where the leak is. Don't be tempted to put your fingers over it. And that goes for all pneumatics. Considering that you can pressurize pneumatics into the thousands of psi, not a good idea. Hmm. Yeah, it'll do that too. One of the typical things that you see a lot in manufacturing is is something kind of like that, where you wrap something around it and see if it picks a hole in it. They also can have like giant tubs of water where they'll submerge things, and what they're looking for is bubbles to be, rushing out of any place where they're trying to test for air. It's a very, very simple, easy way to test anything because if you're looking for something to be completely sealed, to the point where it's not going to release things into the air that should not be there, is to use water, because water shows a lot of things. Okay, so then you also have the liquid line. This goes from the condenser to the receiver, and the receiver to the expansion valve. This is the stuff we saw that was carrying liquids. Carries at a lower temperature of 90 to 120 degrees. Still not really safe to handle, but it's a little bit better than what it was. Still at high pressure between 100 and 400 psi. Okay. Again, not something you really want to get across. Could be very dangerous and put stuff where it should not be. Suction line. This goes from the evaporator to the compressor intake valve. It carries a very cool vapor between 45 and 95 degrees, and it does so at a very low pressure of 70 to 80. So that one's not so bad to get across, but again, anytime you're dealing with pneumatics and you don't know where an air leak is, soapy water is best. Don't do your hands. Okay? All right. So before we continue, I'm going to go ahead and say let's take about a 10-minute break. So this is a decent guide to kind of what you should see. So on the inside of your house, you have evaporator coils. You have your blower that's supposed to blow air into wherever you're settled. So it blows air through those evaporator coils to cool your air. And then it takes what's used, pushes it into the compressor. The heat goes through the compressor out the other side. You have the air that has to be pushed through. So essentially, this is how this works in your car. Okay? This is essentially how your car works. You have blower motors that push air into where you're sitting through the evaporator coils. What that's supposed to do is cool the air in your car. Have you ever noticed it kind of really gets cold right at the vent, no matter what temperature you set it at? So once it finishes blowing that cool air to you, the fluid comes out, goes to the compressor, which compresses it again. It sends it through through the heat exchange, comes out and moves through. It's just a closed loop system. It goes perpetually. Okay? So these are some different valve symbols. Again, these are specialty valves. So you have the airline valve, the safety valve, which everything always has safety valves, right? What do you not want to do with those safety valves? Don't ever want to override or damage them. Safety and pressure relief valves are there for a reason. If you just damage them or destroy them, how many of you watch Mythbusters? How many of you have ever seen them blow? They don't even blow it up. You can't really say they blow it up. How many of you have ever seen what they do with the hot water tank? Where they set the thing to heat, they heats over time, and then what happens to that hot water tank? It turns rocket. All because they do what? All because they take away the safety devices. Don't take away safety devices. Bad idea. So you've got a pressure reducing valve. You've got the cock valve, the quick opening valve. You've got two-way control valves, solenoid valves, three-way control valves, and you have some valves that are pneumatically controlled. Again, these are not totally specialty to ACR, but these are a little more specialized for them. Does that make sense? Okay. These are definitely specialized just for them. Hold, please. Cut down some of the noise. Okay. So these particular ones are a little more specialized for ACR. You've got an air eliminator, you've got expansion joints, you've got your refrigerant filter and strainer. Again, anytime you have any type of hydraulic or pneumatic set, what should you have in there is always the filter, right? I don't care what you're doing or what you have, what kind of system you have. If you have any kind of an enclosed system, anytime you have a type of enclosed system, you should always, always, always have a filter of some sort built in. Why? Because it takes nothing for any type of fluid to pick up something that it shouldn't. I'll give you an example of that. Most times whenever they're canning food or they're making any kind of product to be consumed, they've got to run most of those products before they put them to shelf through a metal detector. Why? Because some sort of something might have gotten caught up in that process and ended up in a can, right? Last thing you as the consumer want to do is open up that can and find what? Find something in it that shouldn't be, right? Another, for example, this happened a few years ago to me. When I first moved into the house we're in now, I came home and the painter told me, your toilet's broken. What had happened was, I don't know how many of you have ever actually examined where your toilet is and where the water line connects. Where the water line connects to the wall, there's a little valve that you can turn on and off to turn the water off to your toilet. A little fragment of metal about yay big had gotten caught in that valve and broke it. Just a little piece of metal. Random piece of metal, nobody knew where it came from, nobody knew how it got in there. It does not take much for random things to find their way into your pipes. So it is always a good idea to have a filter or strainer of some sort to help deal with it. You have vibration absorbers, you have oil separators, you have line filters, dryers, and heat exchangers. Excuse me. And again, a lot of these are very specialized just for ACR or applications through which they're used. Okay? So you have refrigeration component symbols. These are done a couple different views. You have your compressor and centrifuge. You have the evaporator. These are the fin types. So what do we mean by fin types? Well, it means that if you were to look at them from the side, what you would see is something a little like that, whereby if you've ever taken a piece of paper and folded it into a fan, y'all know what I'm talking about? That's how the fin types are folded. It's just like that. And what they do whenever they make these is that you have a line for the whatever it is to run through it. You got fins on either side of these lines. And the fluid passes through those. It's moving back and forth. Those fins are what pull and dissipate the heat from those lines. Okay? Does that make sense? And yes, I do watch a lot of How It's Made. So you have a condenser that is water cooled. You have cooling towers. Now, cooling towers are they're specifically big building. They're not going to be something you see a lot in residential or small commercial. You definitely won't see it in your car. They're I think we have a couple of them here for, I think, a building, but they're not that common. You have what's called spray pond. We'll talk about that another time. You have the symbol for an electric motor, where the number can indicate the horsepower. You have gas turbines, steam turbines. This is to let you know that this would be if you have a separate engine. So you have something, let's say you brought something to a job site that has an engine of some sort to run a bunch of ACR units. That would tell you that, hey, this is a diesel engine. Don't put gasoline in a diesel engine. You have a receiver, vertical versus horizontal, condenser. This particular one is evaporative. So what they do with an evaporator condenser is very similar to the fin type, except that the way this one works, a couple of different ways. One of them is that they actually spray the condensers and help use that to help pull the heat up, and a couple of other ways. Air-cooled forced air, and a rotary compressor. There's a lot of different ways to do condensers and evaporators. Why? Because there's always a different way somebody wants to come up with that they think is better. Some of them are. Some of them are. All right. Cooling the gas into a liquid. So forced air, you have what's called a forced air cooled heat exchanger. That is used for residential, small commercial, and vehicle applications. So in other words, it sticks to the smaller side. Okay? So we use forced air for our homes, apartments, what have you, our vehicles, and most small commercial. What do they mean by small commercial? What do y'all think? Huh? So small commercial would be a strip mall versus the Galleria would be a major commercial. Does that make sense? So think about having to cool the whole Galleria versus just like a small commercial. Let's say a Great Clips. Everybody knows what Great Clips is. It's haircut. Everybody knows the size of a Great Clips. It's a very small little space, right? So small space versus Walmart, right? That's a big space. That would take a whole different way to cool it. Okay, so forced air it's not really covered in the textbook, but it is one of the most common types you would come across. For the bigger application, you have the water system heat exchanger. You have a couple of different types. You have the condenser cooling water loop. This uses water to cool the condenser. The hot water from the condenser goes to a cooling tower. So essentially what happens is, erase my little marks here. All right, so the way you're looking at a condenser cooling water loop. All right, here's my condenser. The water loop goes across all this. What the water's doing is pulling the heat off of the condenser, and it goes back to a cooling tower where it comes back and does it again. Not the best representation, but I'm not a very good artist. So that is essentially how that one works. Then you have a chilled water loop, okay? Where it just passes through a chiller instead of in the air. And this particular one is piped through air handling units. In the book, they're calling it air conditioners. I don't know why they call it something different, but they're not correct in doing so. Okay? Typically, they're called thermal units. So it's usually water, forced air, or cooling tower. So again, a cooling tower, all it's supposed to do is just help dissipate the heat. If you want to really think about a big cooling tower, think nuclear power plant. You know the big hourglass cooling towers they have outside? You all know what that even is for. Essentially, yeah. So the way a nuclear power plant works, you have all this air right here, cannot really escape up that, right? Can't really escape up the tower. But the heat moves up. You have a lot of condensation that comes down and cools here. So what happens is that the heat rises and the cool air stays down here, condenses. It's a condensing loop. Does that make sense? That's how cooling towers work. Is essentially hot air, just like anytime, like hot air balloon, right? What happens to hot air? It rises and expands. Cool air falls to the ground. That's why if you're ever looking for the coolest spot, where is it? It's on the ground, right? All right, so So building A on this campus does use this system. I'm not sure where they've got the cooling tower set up, but yeah, apparently I don't know if they even still use it. They might have renovated it lately. So a forced air system is exactly what it sounds like. You're forcing air over the coils to try and blow away heat. You're trying to blow the heat away. You're saying, go away, heat. You're trying to constantly blow air over the coils to make the heat go away. So think about a hot day. You take a fan and you're trying to what? Blow the heat away, right? That's forced air. Then you have your condenser water loop. Again, there's some units that they actually spray water on these to act kind of like your sweat, right? Because what does water do? Water is a great heat exchanger. Y'all know that? Water does really great at heat exchange. Water likes to pull heat and it likes to dissipate it. Air is not as good at it, right? That's why when you're trying to cool something real fast, what do? Do you sit it outside in the air or do you dunk it in water? You dunk it in water, right? If you're trying to cool something down real fast, dunk it in water, let it go. Water does really great at pulling heat. That's why sweat is supposed to work so efficiently, except whenever you're at 100% humidity. Condenser cooling water loop. Again, this is kind of what I was talking about earlier. So you still have the same system with the compressor and all that. What you also have is a secondary system that forces air out, forces liquid out. It goes over the coils, absorbing the heat before it goes back to its own cooling tower where the heat is released. So instead of forced air, you're using the same principles as the other one. It's just in a closed loop system. Does that make sense? So essentially what they're doing is they're just using the same principles we were talking about. Water likes heat. Liquid itself just likes to have heat. So what they do is they pump it over the heat system here. It pulls up all the heat and takes it back home. Okay? The freon's never released. You don't want the freon out. This is not freon here. This is, it can be water or it could be some other fluid. Generally it's water because water's cheap. What they're doing is they're forcing water over the coils. As it forces it over the coils, the water sucks away the heat from the other side of the coils. And then once it makes it back to that water tower, it releases that heat and the cool water falls to the bottom and gets sucked back into the system. So that's this system right here, and no, we do not generally release it to air, simply because, like I said, freon's chemicals. We don't want those out in the environment. Yes, it's just blowing through the tubes and piping. Excuse me. So the chemical is the coolant. If you got something that's really super cold, essentially all you have on what's going on, okay, I think I know what you're asking. So let's say you had frost on these lines. You're asking about that, right? What is going on is that the internal temperature is so cold that it is actually freezing the moisture that comes in contact. You don't see that a lot in summer because it just doesn't get that cold, but you would see that in the fall or spring whenever it's not so hot. All that's going on is that this is just a lot cooler than the outside temperature. And that's why you would have frost on that. It's not anything actually escaping because we seal these systems 7 ways to Sunday. But what it is trying to do is just kind of still run through the piping and everything else. The fans that you see used, excuse me. So the forced air, we were looking at a couple pages ago, right here. This is the one that's typically in your house. Because what it's doing is that, all right, we can use the air in here for a reason. So this vent up here, right? In your house, you have the holes in your ceiling and stuff like that. That is the forced air return. Okay? What that's doing is sucking in the hot air that is made it to the ceiling and it is sending it back to your unit. Okay? The forced air out, the cool air supply out, is what's coming over here. What you're not seeing is the fact that essentially all that we get is this air right here, the stuff that's blown off the coils. Okay? because this whole system is set somewhere else. We use ductwork to bring that cool air through a building. We don't want to drag all this through here because that would not really result in anything good, and it would be very expensive. What we get in the room is this right here. Okay? This is the main system. There's a secondary system that sits on top of all this. So what we get in our house is you have a very small unit setup that does all this. You have a secondary unit that takes the cold air and sends it out versus the hot air it brings in. That's what that's for. Does that kind of answer your question? So all we get is the air that's being blown off these coils. Okay? Outside your house, where you have the big metal tower that everybody has to buy, that's where this is happening right here. What that's doing is the hot coils are down at the base of it, and it's trying to force air over it to cool it. Does that make sense? That make a little more sense? Okay. So in your car, again, you have the same thing. You have your condenser fan that's blowing air over things. You have the air that's getting blown into your cabin. You don't get to see most of this. Nothing? No. Yes. It's just like, what is the difference between name brand oil and basic oil? 050 is still 050, no matter if it's name brand or not. They can add some small little additives to it, but it's still 050. That is two totally different things. Because vegetable oil, canola is an actual plant on its own. Vegetable oil is a blend of several different vegetables. Kind of like olive oil is strictly olives. So that's kind of the difference there. So that and canola oil is actually not edible to some people. I'm among those. Not edible. Yeah. Yeah. It does not agree with most people's systems. All right. So this is a mock-up of some chilled water loop coils. Okay. So you've got your air-conditioned room. This is what I was talking about. You have your whole system out here. Okay. This is the separate system that's run through all the duct work. All the main work is done separately. We just get the byproduct of the cool air being blown over the coils. Does that make sense? Yes. Yes. You can overfill any system. Just like you can put way too much oil in your car, you can put way too much gas in your car, you can put way too much of anything in any system. If you really want the simplest terms, think kid in a candy store. They eat all the candy. What eventually happens? They eventually, it's got to come out one end or the other, right? Same thing with oil, same thing with gasoline, same thing with refrigerant. If you overfill any system, you're going to bust a seal. It's got to come out one way or another. Either it'll come out the main valve or it'll come out, it'll crack something, it will break a seal, it'll, worst case scenario, let's say you put way too much oil in your car. All the seals, when they mean that the seals blow, there's one of two ways that that can happen. The seals in your car are not very thick or very durable. Most of them are made of cork and rubber. I know that because I worked at a car repair place. So most of the time, here's your base component, here's your seal, very, very thin, and here's the secondary component on top of it, okay? What they mean when you've blown a seal is either you've busted one of these, you've got a crack in it where you're just leaking things everywhere, or you've actually, like torn open all parts of the seal. Yeah, that happens quite a bit, believe it or not. So what essentially ends up happening is that this right here will not seal anymore. You're going to get fluid coming out of that place. Okay? Now that doesn't sound like a big thing because, well, most of the time they're pretty tight together. Except for the fact that you lose pressure. You lose pressure, you are in a lot of trouble because if you don't have something sealed together and holding that pressure to where it's supposed to be, things don't work right. Okay? So if you put too much of something in the system, most of the time things don't seem to happen initially. And it really depends on how much you overfill it. Think balloon. If you overfill a balloon just a little bit, it's just hard to tie off, right? Continue to overfill it. What happens? It's going to pop. So overfilling a little bit, not too bad. Overfill it too much, catastrophic failure. And that's any system you have. You overpressurize or overdo any system, you could cause total catastrophic failure. If you cause total catastrophic failure, there's generally not a way to put Humpty Dumpty back together. That makes sense? Okay. Did I answer your question, by the way? Okay. I wanted to make sure I answered that question. That's actually one that most people don't think about a lot is just what happens if you put too much of anything in the system. Because we all think, oh, it's okay, we can just add a little bit more. Sometimes that little bit more takes it from the edge of catastrophic failure to over catastrophic failure, and you have created your own monster. It happens more often than you think. Truly does. So this is a cooling tower loop versus a chilled water loop. Again, they don't really seem to be that much difference. I'm not sure if that's correct on what that is, because that, they've got the lines running a little bit wonky to me on this one. I'll have to take a look at that. Air distribution subsystem. So this is what pumps air into this room is a subsystem of the total system. Okay? So this distributes the air from the evaporator to various spaces within a building. A lot of older buildings have what's called a dual duct system. Most buildings that are newer don't. Why? Because why would we want that? Because what a dual duct system does is it runs both a hot air and a cold air. Not too bad, as long as you can get the mix right. However, if you start boiling more hot air than cold air, you're going to broil the people inside the area. So this is not something that's done anymore. You'll find it in older buildings because they thought that was the efficient way to do things. It's not. You really want to know the truth. Think about it this way. How many of you have ever seen where you have a hot water tap and a cold water tap side by side? Y'all ever seen those? Why don't we use those systems anymore? Because they're inefficient, right? These days we have what's called a mixing valve that's on the underside of the sink. What that mixing valve does is it takes the hot water you summon and the cold water you summon, it mixes it together so it's an even blend of hot and cold before it puts it to the tap. Does that make sense? We do the same thing now in our homes and in everywhere else. Is instead of, well, I've got hot air here, cold air here, and they fight it out. You know? And sometimes the hot air wins, the cold air wins, and it's just a constant battle to try and balance out. We instead balance it out beforehand, and then it's pushed into the room. Does that make sense? So this system right here is obsolete for a reason. That's just because it's good on paper, not in theory, not so good in practice. In theory, it allows you to totally heat an area, totally cool an area, or mix it. In practicality, it doesn't work that way. You end up with scalding water coming out of one tap, you end up with freezing water coming out of the other, and trying to mix them yourselves is not feasible. What's easier is just to have something mix it beforehand before it gets to you, and you get something very consistent. All right. So this is essentially, how many of you have seen the big giant heating air thing in your house? This is how that works. So you have your big major unit here. Okay, you got the big blower at the bottom. What's that doing is it's pulling air from the house and blowing it back up through the coils. This is your heat exchanger right here. You have the, if it's gas powered, this is where all the gas burners are. And then you have this area that goes up and supplies the air to your area. So essentially that is, in a nutshell, exactly what's in your basement or in your utility room. How many of you have ever seen that thing? A couple of y'all? Everybody actually wonder exactly what you're looking at. Now you know. So some ducting symbols. You have basic duct, you have exhaust sections, you have what are called splitters, dampeners and all that. Because what most people don't realize, and I'll be quiet here in a second so you can kind of hear it, air duct is very, very loud, especially when you start splitting the air. You have turning vanes, supply outlet with a ceiling diffuser, shows you direction of flow, supply duct, access doors. Do we have access doors to most of our ductwork? No. Most of our ductwork looks like this. It's not something that a human being can get into. It's not like the movies where every time you turn around there's another section of ductwork somebody can get into, and crawl through a building. Which, by the way, that would be really noisy, and it will not support most people's weight. This is not Mission Impossible, right? I can all but guarantee you they are doing that on the ground because actually getting into ductwork is very hard, would not be pleasant, and would be very, very loud. Okay? If you're trying to sneak through ductwork, people will hear you a mile away. Everybody will hear you moving in the ducts, and they're going to sit there and go, "What is that sound? Why is somebody messing around in there?" It is not the "I'm quiet, everybody knows where I'm at." It's bang, bang, bang because it's saying the forms. You can kind of hear it, right? You hear how the air is moving in the ducts? Yeah, that's why you would never be able to crawl through ductwork. So Mission Impossible, not so possible. You have to find another way in the building. Which I don't know where that particular set came from. I've always kind of wondered who thought that you could go crawling through ductwork quietly enough to be a cat burglar. You'd alert everybody in the building in 5 seconds. Because if you've ever taken a cookie sheet and like bent it back and forth and heard like where it makes that thunder sound, exactly what that would sound like. So you have double line diagrams and single line diagrams. Again, this mostly becomes more obvious in everything in trades. What you're seeing here is a double line diagram, essentially showing you ductwork comes to where it blows out here, ductwork again, moves to another room, and then there it splits to 2 rooms. You got it coming up here and splitting here. It's got the lengths and widths of everything. I'm trying to show you exactly where everything is supposed to be. Okay? Single line drawing says much of the same thing, but it does it in a different sort of language, you can say. So control subsystems, because we have to control the ACR that comes into a room, because otherwise you can make the room too hot, make it too cold. You have heat in the middle of summer and freezing cold in the middle of winter. So we have direct control, which is self-contained control. So this works in direct response to the effect of the system on the control device. So most thermostats have a sensing element in them somewhere. And what that's supposed to do is alert the system, say, hey, hey, it's getting too hot. We need to shut the system down. Or hey, it's too cold. We need to set it to where it doesn't do anything. Right? So no electrical on pneumatic systems between the sensor and the control element. Most refrigeration systems use direct control. Why? Because it's the most efficient way. Indirect control has an electrical or pneumatic system between the sensing element and the control element. Sensing element provides information to the controller. Controller operates the control. I can't say that most refrigeration systems use direct control. Most air conditioning systems use indirect control. So refrigeration systems, that's your refrigerator at home, right? What that's supposed to do is supposed to remove heat out of there and keep the humidity at a certain level. And you don't want that thing constantly running because it's kind of loud, right? ACR, you have the control that's talking to the sensor and talking to other things, and it's constantly telling it turn off, turn on, room's too hot, room's too cold. Basically, it likes to complain to the rest of the system and say, fix it, right? All right, so this is a direct control system. So you have your evaporator, and it's talking to your compressor. You have your receiver, your condenser, with your gauges. This is all dealing with hydraulics and pneumatics here. So with direct control, we have thermostatic expansion valves, which they give you the full definition in the book. You have what's called an ADR valve. You have automatic controls and manual controls. Okay. We've kind of gone over that when we were doing the questions and answers earlier. Control diagram for hot and chilled water system. So you have different valves everywhere. This is the hydraulic and pneumatic controls for the system. And then you have the electrical symbols for the refrigeration system. Factory wired, field installed. Why is there a difference between the two? Why is there a difference between factory wired and field installed? The way it came versus the way you had to install it, right? There is always a difference, isn't there? Kind of like whenever you install a light. How many of you have ever installed a light fixture? You got how the factory made it and how it came. Does that mean that's how you had to install it? No, because everybody's wiring is, let's face it, this is Alabama, everybody's wiring is different. Because the factory, I'll put it to you this way. Y'all know what I mean when I say some people have different switches for the light versus the fan? If you install a fan fixture. Some people have only one that controls both. That's where you have to know factory install versus field install. Okay? You have different switches. So these close. This one closes on the rising level. This one opens. Closes on pressure, rises on pressure. Okay? All these are just telling you how the particular valve will work in conjunction with your system. So just like the float sensor in your toilet that opens whenever you pull the lever and it immediately closes, but the water level rises until that float, what? Until the float gets to the highest point of its journey, right? So this is a wiring diagram, not a ladder diagram. Ladder diagram would have side 1 and side 2. This is a wiring diagram because you've got your power supply and everything moves from there. Everything is fused on this, and then you've got contacts and overloads over here. This, you've got your condenser 1, condenser 2, and your compressor. Okay. You've got a point-to-point diagram. This one's very set up here. You've again got your colored wires you got to look for. This is a connection wiring diagram versus a ladder diagram. Okay, so these are two totally different types of diagrams. This one is your ladder diagram. What is different between this and this? This is very, very simplified. Okay? About as simplified as you can get. All it's showing you is these are connected back to your power source versus your neutral. and what is connected between the two. It's not showing you point-to-point connections like this, like the first one is. Okay. So you've got electronic control systems, diodes, transistors. We've already kind of gone over a lot of these. This is a basic thermostat schematic. In other words, how the thermostat in your house is wired and set up. Pneumatic control subsystem setup. Y'all got any questions about any of this? All right. So chapter 10, you need to have 5 questions, 5 answers on Monday. I will be trying to go over the test on Monday. I'm trying to think of anything else. If y'all have any questions about anything, let me know. Like I said, I'm going to try and get that test graded as soon as possible.